Right. Hi, everyone. Thank you for attending. My name is Telmo Oliveira. I'm a data engineer at Toon, and I'm here to talk about using Sparks in the cloud, or at least how we use Spark in the cloud. For those of you unfamiliar with the brand, Toon is in the smart energy area. We sell different products and services like smart thermostat, monitoring for solar energy production, and energy bill breakdown. We're present in around 350,000 countries. We're present in around three countries, namely the Netherlands, Spain, and Belgium, and we have presence in around 350,000 homes. We started back in 2004 in Amsterdam. We did several energy-related products, but in 2008 we decided to focus only on smart thermostats. And in 2015, we were acquired by Eneco, which is a major energy company in the Netherlands. And that was our first tenant. And this is a good time to introduce the tenant concept, at least to justify some of the architectural choices that we took. So the way we reach consumers is by partnering up with major energy companies across Europe, and we make our products and services available through them. So for the scope of this presentation, when I mention a tenant, I just mean one of these partners, like Eneco for the Netherlands, or Fiasco for Spain, and Electrabel for Belgium. Since this summit is heavily related with data, I thought it would be interesting to at least make a depiction of our data sources. We have data coming in from both gas and electricity measurements. We're proud to say that we work with a high-resolution data, at least for the electricity case. It's 10-second data. If you have a solar panel, we also do some monitoring on those, and for us, these are just meter modules. We also have some boiler modules to monitor hot water usage, and all of these hook up to the displays on people's homes. The displays have some local usage metrics, and they also can be paired up with third-party products like the Philips Hue lights or smoke detectors or smart plugs. And our mobile app. There are all kinds of supporting services that are not that interesting for this presentation, but I'd like to focus your attention on the rightmost part, on the user groups, namely the Innovator subgroup. That's where our journey started. Halfway down the line, people in the company started to realize we were in a position to work with quite a unique data set. So to explore any possibilities with it, we set up a group of friendly users, which were the Innovator group that I mentioned a while ago, from whom we could not only collect the data, but also keep in touch with to validate any potential business cases. After a few attempts, we noticed there was a clear potential on personalized energy insight based on users' behaviors. So users related with services that were catered directly to them, like which one of their appliances is taking too much energy. As this initiative became more successful, we decided to invest on some proper infrastructure to handle all of this data. And that's when we had our first Hadoop cluster. There were a few iterations on it, hardware and software-wise, but in its final form, we had a 12-node cluster with a managed distribution of Hadoop. It was purely an explorative environment. There was no guaranteed performance, and there were very few business SLAs. We just ran some data analytics and a few scheduled data flows like data ingestion or ad hoc data sharing with one of the tenants. But at a certain point, we were hitting our limit. We had more critical scheduled business flows, like some proper SLA with a tenant, like every hour, share the raw data with the tenant where their data was originating from. The data science team grew. They grew in number. They became much more demanding and sophisticated in the use, especially as they moved from local Python analysis into Spark. And there was an increase, this posed an increased strain on the cluster, and there was just not enough horsepower to handle all the ETL flows and the data science flows. And things became really unmanageable as hardware got older and started to fail. At the same time, the number of users who were sharing their data was about to have a massive scale-up from the low thousands into the hundreds of thousands. We now have around almost 20 terabytes of data, but we collect around 100 gigabytes per day now. So we'll double that size pretty quickly. There was also a ramp up in the development of the personalized Energy Insight app that I mentioned a while ago. So it was clear we needed some other setup. As we discussed what the new platform would look like, there were a few requirements. There needed to be a seamless transition, so we needed to maintain our current SLAs. As the processes became more critical, we needed to make sure that we collected data anonymously. We had a contract that was about to expire with the on-premise data center. There was a clear deadline, so we had to move fast and optimize later. We needed to ensure that we could accommodate several tenants on the new platform, and this was paramount, as little disturbance as possible to the data science team. This last item was actually so important that we tried to see what was actually used, because our problem with the managed Hadoop distribution is that with it came a plethora of products and services that we didn't directly use, but we still needed them to be there to manage the distributed functionality. Things like Zookeeper or Solar. We didn't directly use them, but of course they needed to be there to make sure the cluster ran properly. So as we started our assessment together with the data science team, we noticed that we just made use of three services, the Hive, Spark, and Jupyter Hub. By Hive, I just mean a SQL-like interface to query the data, regardless of the execution engine, could be MapReduce or Tez. In our case, it was already Spark, our default choice. We definitely needed Spark, of course, and we needed a friendly interface on which the data scientists could explore the data, prototype on, and share their results, and that's Jupyter Hub. This is all we wanted, really. We did not want to manage services and processes in the background. We wanted to focus on bringing business value. So after some proof of concepts and trials, we decided to go for these two things. AWS was and is a pretty standard service. It's not going anywhere anytime soon. And the rest of the company was actually moving to AWS as well. And there are advantages in using a common set of tools. So we decided to piggyback on that initiative and move along with them. And we also had a very big restriction at the time, was that Databricks could only be deployed on AWS, at least back then. So why did we go with Databricks? The other alternatives were actually quite good and mature, but with them came extra tools and services that we didn't need, but we would need to monitor, to provision, to maintain, and we'll be going back to exactly the thing we wanted to get away from in the first place. We like Databricks especially because of how little ops we had to do. A lot of work was done for us. They catered a little bit more to data science teams, but we just view them as managed Spark clusters. There were other things we especially liked about them, though, namely the cluster timeouts. It's always the case that every now and then we have an ad hoc request, some unforeseen workload, some data scientist needs a isolated environment, like a sandbox environment. But then due to human forgetfulness, someone forgets to shut the cluster down, and it's just burning money through the night. And you come in the next morning, and that's when you notice it. And with a cluster timeout, you can just say that after X amount of time has gone by with no usage, just decommission, and there's no external action required. We liked that auto-scaling was a breeze. We only need to set a maximum and a minimum boundary, and based on the usage, the cluster scales up and down. Especially scaling down, there are a lot of platforms that don't do this quite well, but for us it was things just worked out of the box. We didn't need to flag a certain node and stop sending tasks into it, wait for those tasks to finish and decommission that node. That was all handled for us. Spot instances, they handled quite well, and we like the concept that we can bid not on an absolute price. So it's one optimization problem that you don't need to tackle. We only bid on a percentage of the on-demand price. So if you want to just make things simple and say, I'll pay 100% of the on-demand price, if that threshold is crossed, you just roll back to using an on-demand node. And, well, it's also nice to work with such a well-documented API. Back to our move, we followed the approach of having infrastructure as code. and this would ensure us repeatability. As a new tenant is onboarded, it follows the same deployment logic as the others, and this was especially important for us because we expect to onboard new tenants as time goes by, and we don't want to have a specific deployment for one of them and then another deployment for tenant B. We'd like them to follow the same tracks. We also wanted to ensure there was a fast deployment logic, no UI to click through, no unique names to come up with, no forms to fill. This is all automated. Things are also resilient. We can make it as highly available as we want, and to put it in kind of a silly way, it's easy to press the restart button. In case something doesn't work, you can just redeploy your infrastructure again and things will look the same. And there's also the advantage that your documentation now is part of your code. It's live, it's on version control, and it's not becoming outdated on some internal wiki page. To achieve this objective, we use two tools, Terraform and Ansible. With Terraform, we deal with the underlying infrastructure, how everything is put together, and once that's done, we resort to a few Ansible playbooks to automate the final details of our configuration. When doing this kind of work, there's always the question of how to handle critical information like tokens or passwords or usernames. And for that, we use AWS Parameter Store, which these tools query on the fly. So there's less need for you to host yet another service which would handle critical information. And now there are no passwords on users, on developers' laptops or on source control. So before we had a very error-prone process, and now everything is predictable. With Terraform, all of these things, by the way, are per tenant. We provision things like the S3 bucket. We have one for raw data with a policy to move to cheaper storage as the data becomes more infrequently accessed. We have another one for logging, another one for staging, and the process data. This is where our typical Parquet files lie and where the data science tables are. We also have some EC2 instances where some web apps run, but more on that in a little bit. The network topology, this was quite a big one for us. It can be quite complex to handle the setup of VPCs, address ranges, public or private subnets, route table entries. There are peering policies, net instances. This is complex to tackle every single time, but we only had to deal with this problem once, and now everything is scripted. We also have some log management infrastructure. That's just a typical Elasticsearch Kibana setup. We have some RDS instances where our relational databases are, and more importantly, where we host our Hive metastores. And we also make heavy use of IAM roles and policies. This is what makes sure that infrastructure meant for tenant A does not peek into the resources of tenant B. This is just an example of how we deploy things. We have a wrapper script around Terraform, but we just say which component of our infrastructure we would like to redeploy, and the target argument, that's just the tenant names for us. So we can switch that by tenant A or tenant B, and everything will be deployed as a clone of other environments. With Ansible, we use it due to its vast module systems. We do user and group management, databases and ACLs. So once we have a new pristine environment, data has a certain schema. There are databases, there are tables, there are columns, there are field types. We manage all of this with Ansible. And we also have some custom app deployment for which we use Ansible for. Same as the previous example, this is how we deploy the infrastructure. We just state our playbook, and the target is only the tenant name. And this is the end result. Focusing on the green box, we have different components making up a standard tenant deployment. Data is sent from this place to the Elastic Load Balancer, and until recently parsed with EC2 instances, but we very recently moved to Elastic Beanstalk, so we don't need to oversee yet another Linux box. Data then lands on the raw data bucket, And then we have a policy to replicate it to a shared data bucket. So if we have a third party, like the tenants, who'd like to use that data and run some analytics on that data, we don't have an hourly upload process. Now they have a live snapshot of what the data looks like. All the engineering network traffic goes through the Bastion host, and we can reach services like the scheduler or the MySQL databases. And when a user gives consent to using personalized data for a specific service, we interface with a tenant-specific cloud network that we don't host ourselves, which is the blue box above. The last thing to mention is that little VPC box below. That's where our Spark clusters are. Focusing on the scheduler for now, this is probably the most important thing on ETL, when to run what, run something once or twice per day or per month or per week. And some typical flow for us would be to intake data every hour, filter out some uninteresting data, probably run an anonymization step, and then aggregate everything into a statistics table. We use Airflow for that. These are just 2 screenshots from their website. All of the data science tables or enriched data are generated through a process triggered by Airflow. And we really like the concept of expressing the scheduling logic through a DAG because we have several dependent steps. And this way you don't need to guess that something takes 30 minutes, so you leave a buffer, so start the following step after 45 minutes. This way you can say for step D to run, C needs to be successful, and for C to run, A and B both need to be successful, something like what you see on the diagram here. Everything we have follows a schedule, everything but the main data intake. For that, we actually use Spark structured streaming. And in that way, we kind of simulate a real-time data ingestion process, but it's only listening to an S3 directory. But as data comes in, it immediately lands on a raw data table. This framework that Spark provides made the transition a breeze for us because we only needed to change a few lines of code from the batch process, and now we are able to emulate at least the Kappa architecture because there's almost no distinction between doing batch processing and stream processing. There's no Spark processing directly on this machine, on the scheduler. This is only a service that does a submit to a remote Spark cluster, one of those that you saw on the previous slide. All of our ETL processes are implemented using Scala, but the scheduling logic, that's expressed in a YAML document, and we created a separate project for that, where we feed this XML file and a Python, an Airflow DAG in Python is spit out, and that's the file we need to deploy on Airflow. The Scala code is not that interesting to demo because it only does some routine work, like querying an endpoint to get an authentication token and use that token to query another endpoint to get some data and serialize it into a table. But it's probably more interesting to see how we expressed our DAGs. I pasted some snippets here. We have the DAG ID and the scheduling logic, how frequently should it run and how many parallel runs we want to have. The tenant is purely an argument. We only need to change that name and everything works just the same as the other one. You can specify the location of your jar. Even if you use S3 or JFrog Artifact Factory, we just have kind of like a unique resource domain name for that case. This is what a typical task looks like. We have a certain task that will run a class. There are a few arguments that we need to pass. And below, you can specify your dependency. Before this task runs, this other one needs to be successful. And that's how you build your DAG. This is an important point. We tie everything together on our ETL flows with cluster creation and deletion. So before any job starts, a new cluster is created, then the DAG is run, and then the cluster is deleted. And this keeps the environment very, very clean and makes all operations idempotent. And the recent per second billing move from AWS really helped us on improving our workflows and moving completely to this ephemeral cluster approach, because now we no longer need to reason on how to optimize our system for the fully paid hour. Now we just pay for what we use. Every Spark cluster is only processes ingested Parquet data, but if someone makes a mistake, that's just processed data. So it's easy to press the restart button and the raw data is processed again, and we have a snapshot of the table again. We also customize a few other things on Spark, especially on cluster creation. Something that's actually not listed here, but we make use of, is the cryo serialization, which was mentioned on the previous talk. More importantly, we have make use of an external Hive metastore for two reasons. Number one, even if clusters go down, the Hive metastore, it's always there. It makes the infrastructure more resilient. Also makes it accessible for other services to use it. And also because the data now is secured not only through the machine roles, where they cannot look into other buckets, but also because one cluster can only know about the tables and databases of that Hive metastore. It cannot know about the tables and databases for tenant B. We also have our logs being outputted to S3, and then a notification is generated from it. We have a Lambda function that picks it up and parses the relevant information and sends it to Elasticsearch. And Spark logging can be really verbose. So on our jobs, we set the level of logging to warn, at least on a few categories. Authorization can be a complex setup of things. So we have users that are part of groups. Only specific groups are allowed to connect to specific clusters, and the clusters connect to external Hive metastores, and they also have roles attached to them. So this is quite a dense mesh, but we're really able to fine-tune a very precise purpose for one cluster, which makes things really secure on our end. And we also use this type of node. It's usually the case that Spark is quite memory hungry, but it's not the usual case that the entire data set fits into memory. You need to have quite a big cluster, so there's always the spill to disk. And we decided to go for a more generous node with a generous local storage, and we saw a lot of performance improvements by using this type of node. And this way we also skip the overhead of going through the network and data landing on an elastic block storage, which is usually what you need to do if you use something like an R4 instance. For the future plans, I can imagine being questions like, why didn't you use a queue like Kafka to decouple all of these processes? And the reason was we didn't need to so far. And we wanted to make sure that before we opened that door, things would be working well on our end. But now that everything is set up, it is much easier to innovate. We are able to move much faster. And we'll definitely tackle streaming in this next quarter as new real-time services become more prevalent. And we're still lacking a more robust CI/CD pipeline. We still have to do some manual steps that we'd like to get rid of. In the end, what's all this for? We only moved bytes from A to B. What's the final objective? The data science team usually picks up from there. And one of the many interesting things that they're working on is on bringing to life an energy-saving app. And to get a sense of the cool stuff they do, Stephen Galsworthy will speak about it tomorrow at 2 on the auditorium, and you get to know a little bit of the business side of things and some of the data science algorithms and approaches that were taken. All of this didn't happen by itself. It was the effort of a team, so I'm giving them their seconds of fame here. And that was it for me. I'm open to any questions. Thank you for attending.
Yeah, so I'm very curious if you experienced any increase in latency moving to a cloud architecture, just in spinning up your cluster and spinning it down each time you need to do something?
Yes, but the answer can be a bit more complex than that. We have two very different use cases. One is the automated workflows that I presented here, but there's also the interactive flows. So there's always a there's always a cluster that's running 24/7.
Yeah.
And it scales from 2 nodes to 30, I think, purely based on the usage. Mainly because of that. We couldn't spin up a cluster for every single data scientist that wants to work on the data. So auto-scaling also made things simple for us. We can just say, this cluster is always here. You guys are free to use it. And if you need some more firepower, everything's taken care of. We have auto-scaling.
Okay.
Thanks.
I have 2 questions. So one regarding the use of Databricks on top of AWS to do the provisioning. And like, for instance, in our use case, we just use the AWS API directly to provision. So the first question would be like, what are the advantages you see of having this overlay on top of the AWS API versus just using it straight up? And the second one is I've noticed that you, in your job, you refer the number of workers that you're going to use for that particular job. And my question was, why not use like on Yarn with the maximize resource usage to have it just expand to whatever it wants and just provision the number of nodes you need as far as hardware goes?
Yeah. So for the first part, we use Terraform. To be honest, the original reason was that we would be able to be cloud agnostic. We only have a Terraform script, and if we want to move to Google, we can do it. But of course, as you get to get lost in the details, you're almost forced to just embrace that specific cloud functionality. So I guess that argument was kind of lost. But we also noticed that we're much more productive using Terraform than in the beginning. In the absolute beginning, we were actually using CloudFormation, but that was just a nightmare to work with. So yeah, we constantly heard that feedback, and it only lasted a few days for us. We also use Troposphere, which makes things a little bit more sane. But with Terraform, we were just very, very productive after the first week. We already have more than half of our infrastructure, so we just stuck with it. The second questions, right? The second question. There are 2 answers to that. Number one, this was for a very stable load, so we knew how many workers we usually need. We could always go for auto-scaling, so set up a new cluster before the DAG runs, and based on the usage, auto-scale between 1 and 10. I guess that to be the main reason. I wouldn't see any other. Well, there's also, this is kind of a hard argument to make, but if you as an organization don't need to reason about processes and operations and when to run what, you just want to make things simple so that you can focus on the next thing. The fact that we just follow one simple rule, every new DAG gets a new cluster, made things really simple for us. Yeah.
We also maintain some ETL jobs in Airflow, and one of our challenges is maintaining dev, QA, and production pipeline. And I'm curious how you guys maintain dev, QA, production data pipeline with all the data and everything. How do you modify and how do you deploy?
Yeah, it's everything is tied up on one limitation that we have is that Databricks is deployed on one AWS account. And we have 2 AWS accounts, one for acceptance, another for production. We might split this up even further later on. But the way we divide things is just we have 2 different schedulers, 2 different Airflow instances. To be honest, Airflow, having a multi-node Airflow deployment, it's not really stable, we found. So we just have a very generous node, one for acceptance and another for production. Then we also split in on the bucket name. So that's part of the argument. If your bucket has ACC on it, you know you're only dealing with acceptance data. And I think this is just it. That's only the parameters that we pass to the jobs. We just say, this is acceptance or this is production. And based on that keyword, we go to another bucket, we go to another Airflow machine. I think, yeah, the network topology is also different. So things are really contained, but we don't make really deep use of Airflow. We just schedule things to submit to a remote Spark cluster.
Okay, it sounds like we're finished. Thanks, Telmo. And the next session starts in 10 minutes.
Thanks.